Hello, everyone. In this video, we will give you a brief overview of the model design and the technical explanations corresponding to the use cases of our project. Let's get started. The first part is system model explanation. We have 3 parts totally. In knowledge acquisition part, using Kaggle, we collected 2 similar datasets. The first one contained course name, university name, course level, course rating, course URL, course detail, course skills. There is totally 3,416 data in this dataset. The second one contained course name, university name, course type, duration, course language, course rating, course level, instructors, course detail, and totally had 6,565 data. In data pre-processing part, we deleted course URL from first one, course type, duration and instructors in the second one to make the data easily to analyze. In order to combine these 2 datasets together, it was necessary to crawl the course language of dataset 1, course skills of dataset 2. We used Selenium to automatically crawl the data from Coursera and store in the dataset. After that, we combined these 2 datasets. Through analyzing, we found some data was shown in different languages. So calling Google Translation API, if the language wasn't English, we wrote a script to translate it into English. After dropping duplicated and anomaly data, we finally got the final dataset. In knowledge representation part, in order to calculate the similarity of each course skills and course detail respectively, we used sentence transformers, which also named SPERT, to get the result. Sentence transformers can be used under different situations, like semantic clustering, semantic similarity, natural language inference, paraphrase mining, semantic search, embeddings, question answering retrieval, and so on. Our using situation is semantic similarity calculation. Compared with BERT, this algorithm adds pooling strategies to make the output in a fixed length. SPERT model can characterize a sentence well semantically, which makes it possible for sentences with more similar semantics to be closer together in vector space in terms of sentence embedding vectors. In this case, we used pre-trained model, or mini-LM, L6, V2 to get the similarity score. Also, for using other course information, we designed a set of rules to quantify the values. The weights were designed by experience. In knowledge implementation part, we converted each sentence, course details and course skills, to sentence embeddings so we could get the cosine similarity of the sentences in no matter list format or matrix format. Using the rules to get the weight, added the similarity calculated above, we could get the final recommendation score of each course, sorting the result and get top 10 recommendation. Technical explanation of use cases. Our system can be divided into 5 main use cases, and we will then explain the data flows and techniques corresponding to these use cases. In the login use case, the front-end sends the user's input to the back-end as an HTTP POST request. The corresponding function on the back-end compares the user's input with the user data table in the database, performs user verification and returns the corresponding result to the front-end. In the registration use case, the front-end sends the user's input to the back-end as an HTTP POST request, and the corresponding function on the back-end accesses the database and compares the existing user data table. When the user's input matches the criteria, the function writes the new user's data in the user data table. When a user sets or changes a preference, the front-end sends the preference information entered by the user to the back-end as an HTTP POST request, and the corresponding function on the back-end calls our recommendation model. The recommendation model will calculate the recommendation result based on the user input, and then the back-end function will access the data of the corresponding user in the database and write the preference and recommendation result to that data. When a user visits a recommendation page, the front-end sends an HTTP GET request to the back-end web server. When the back-end receives the request, the corresponding function accesses the course recommendation results stored in the database corresponding to the user who sent the request, and then accesses the details in the course data table to return information to the front-end page as a Django template language. In the course details use case, the front-end accesses the URL containing the course ID. Upon receiving the request, the back-end accesses the corresponding entry in the course details database. The course details database contains not only the basic information about the course but also the recommendations calculated based on the course. Our recommendation model preprocesses each course and produces a recommendation result for each course. The recommendation result is an array containing the recommended course IDs, which is stored in the database along with the course information and other fields for access by back-end functions. That's our system design. Thanks for watching.